Hi guys, welcome back to Data Every Day. Today we're looking at a data set of human resources data, and basically it's a data set of different employees and various attributes about those employees. We have a column called terminated, or TERMD for short, somewhere around here. Here it is, which basically says if an employee was terminated or not. And we're going to try to predict this column based on all the other features. So let's hop into the notebook. We're going to use a number of different classification models for this task, and we're going to see which performs best at the end. So I'm using NumPy and pandas just to work with the data, and then I'm going to use the train test split function from sklearn, and the min-max scaler and standard scaler. We're going to try them out both and see which works best from sklearn as well. These are for pre-processing. Let's go ahead and import those, and I'll load in the data using pandas.read CSV. And I want to get the file path to my CSV file, so over here I'm going to go get it from here, copy file path, and paste it in, and we can take a look. So this data set has 36 columns, and currently I cannot see them all. That's why we have this ... here. So I'm going to go into the console and type pandas.set option max columns none. And that way, if I refresh this, you can see all the columns at once. And we do have a decent number of them here. I mean, it's nothing special, 36, but it's definitely a good number. Especially, we don't have a lot of data, so it's good that we have some more features to draw from. So there's definitely a good amount of pre-processing that needs to be done on this data set. We have all different sort of data types. You see we have some date columns, we have some nominal columns, maybe some binary columns in there. We're going to try to get all the pre-processing done so that we can feed it into our model. So I'd like to take a look at data.info. Just give us a little more information. We can see if there's missing values, and we can also see the data types on the side. Now I do see some missing value columns. It actually looks like there might only be 2 here. Date of termination has quite a few. About 2/3 of the data is missing. But manager ID does not have many. And a bunch of these columns I'm probably not going to end up using anyway for various reasons. But let's get into pre-processing. So I'm going to create a function called preprocess inputs. And this is going to take in a data frame. And it will start by creating a copy of that data frame so that all of our pre-processing will be done on a fresh copy. And then at the end, we're going to return that same data frame. So if down here I want to call this function, and I'm going to pass in our data, which is this data frame up here, and I'm going to store it in, we'll call it x. So x will be our pre-processed version of data. So currently it's exactly the same, but as we add our pre-processing steps into this function, we'll see the results down here. So the first thing to do, I think, is probably get a better sense of what these missing values are. So let's look at it. There's only two columns. Actually, we can double check that over here. Actually, instead of doing it on data, I'll do it on x. So over here, we'll call it x.isNA, which will basically just generate a data frame that has trues and falses depending on if there's a missing value in a given cell. So then if we sum that over the row axis, by default this is on axis 0, then we'll get the total number of trues, or the total number of missing values in a given column. And so this will give us the actual counts in each column of missing values. And it looks like we were right, there are only 2 columns with missing values. There's 207 missing values here and 8 values here. So let's understand these columns a little better. So date of termination, we got to think about this. What is our target here? What are we trying to predict? So we're trying to predict the terminated column. And because we're using this as our target, it would be sort of cheating to include other features that are dependent on the target. So if we have, well, you can see we have the date of termination, right? This one has missing values in it. However, the reason there's a missing value is going to be if the employee wasn't terminated. So we're only going to have a date here if we have a 1 over in our target column. Additionally, we have a terminated reason. which has a still employed value. So you can see these two columns are actually they're giving away the answer to our target column. So these will have to go. We're going to have to drop these two columns. So up here in our preprocess function, I'm going to drop unneeded columns. And so we can do that with df equals df.drop. We'll pass in all the column names here. So it's these, now let me copy them over here. It's date of termination and term reason that we do not need. So we're dropping these from axis of 1, which is the column axis. And now we should be a little more fair and more honest in what we're using to predict our target. So I'm running this again, getting x now, and if we run x.isNA, you can see that actually those 200 missing values that were in date of termination are gone. And if I run x again, you can see we no longer have that column in here. However, there are these ones remaining, manager ID. So let's go look at manager ID and see what's going on here. So I notice that we have a manager name and a manager ID. So it would be useful to understand how many unique values are in each of these columns, because it's possible we have some redundant information here. As you can see, the same manager appears twice, and you notice that the same ID is associated with that manager. So it's possible that the reason we have missing values is that some managers don't have IDs, and in which case we can just drop the manager ID column. So let's create a dictionary that's going to map a column name to the length of unique values in that column. So I'm taking x subcolumn dot unique, and then I'm taking the length of that. And that's going to give us the number of unique values in a given column for each column in data.columns. Sorry, I'll do x.columns. Alright, and now we can see the actual numbers associated with each column. So we're looking over at manager name and manager ID. It looks like manager ID has 24 unique values, and manager name has 21. So there's actually more manager IDs than manager names. However, we also know that the manager ID has some missing values. So it's sort of our call here, what we want to do. We could leave this on and one-hot encode it. And by one-hot encoding it, that would actually take care of the missing values, because all of our one-hot columns would just contain all 0 entries where there's a missing value. But I feel like manager name contains most of the information that we would get out of this column. Now I can't be sure, but it seems pretty clear that a manager name gets mapped to a manager ID. Now I can't be sure why there are missing values. Let's see. Let's take a look at manager name. So we can inspect a given column by taking that column and typing .unique to see what kinds of values are in there. So okay, maybe this has something to do with it. We have board of directors. Maybe that has some weird IDs. But I think that this is probably enough information. There's probably very little additional information we're getting out of the ID. But I think if you wanted to, we could definitely keep it on and one-hot encode it. But I'm just going to drop it. It doesn't really matter too much. So here it is. We're going to drop it from here, manager ID, and now we'll get that back. You can see now we have no more missing values. So if I sum across the columns now, we'll get the total number of missing values in the data set, which is 0. And so now we don't have to worry about missing values anymore. So we have lost a few columns, but nothing substantial. We still have most of the information intact. We also did away with the information that was it's sort of like cheating by using it. Alright, now let's take a little closer look. So we have 311 rows. And I notice here that we have some columns that have 311 unique values. And what this means is that for these columns, every value is unique. And when every value is unique in the dataset, it's not actually useful to us because there's no sort of information being carried. Now, maybe you could extract some feature that's like first letter of a name and use that as a feature, but I can't really believe that the first letter of someone's name would be useful in predicting whether they'd be terminated or not. So pretty much employee name and employee ID are not useful to us. So I'm going to go ahead and drop those as well. All right, I'm just going to remove these little spaces here. All right, and one more here. And now if we run this, we don't have those anymore. This is gone. And if we check all the numbers of unique values, you can see they're missing from the top. So we're left with this set of features. We can see there's no more in here that have 311 unique values. So everything else is sort of it's sort of fair game for our model. So now I think the encoding process begins. And based on looking at this, it looks like we might need a bunch of different encoding schemes. So we have some columns here with only 2 values. And when we see that, there's really only one viable encoding method. I mean, you could do one-hot encoding, but it's a redundant encoding, because you'd have one column with all ones when a given value is present, and the other column with all zeros in the exact same places. So it's just sort of an inverse of each other. So the best way to encode a binary column is with binary encoding, which is essentially take one value, send it to 1, take the other value, send it to 0. And that's what we're going to do to the sex column, and there might be some other columns in here. We have other columns with 2s, but you can see that those have already been encoded as 0s and 1s. Not this one, but oh, they have gender ID as well. So I wonder if this is redundant then. Can we see? Yeah, it looks a bit redundant. I'm pretty sure they always match. We can actually check this. If we take the gender ID column, which looks like this, and then we also take the sex column, which looks like this, and what I'd like to do is map these to 1s and 0s, so we can apply a lambda function to it that takes some x. Here x is a given gender or sex, and we can map x to 1 if x equals m. You can see that the m seem to correspond to 1s, and otherwise we'll map it to 0. Oh, well, it didn't seem to work. Let me see why. We're going to take this column and look at the unique values. Oh, and we can see there's a bit of white space there at the end of m, so that's why it didn't work. We're going to add the white space in and then rerun this. Okay, now you can see that these are seeming to match up. So what we're going to do is compare them now. We grab this and ask, is it equal? Are both of these things equal? And we'll get trues and falses depending on if it's true in a given spot. But now I want to take that whole thing and I'll ask dot all, which says, are they all equal? And that is true. They are all equal. So we know that we don't need the sex column. The gender ID fully encapsulates it, or it carries all the information that the sex column carries. And in addition, it's already encoded for us. So we basically don't need this. So let's go drop it. Okay. We're still looking now. All right. So the question is, are there any columns in here that have 2 values that actually do need to be encoded? So we can get this basically by we take this sort of dictionary thing, right? This is saying map a column to the length of unique values for each column in x.columns. So let's do something a little different. We're going to grab this again, length of unique values in a given column, but we're going to get a true-false value based on if it's equal to 2. So this is asking, for a given column, is the number of unique values 2 for every column in x.columns. And this will be a true or a false based on if it is binary. So what we can do is now use this true-false array to index x. So x.loc, passing in all rows, and just these columns, which is actually just the true-false array. And so we're using the true-falses to see the actual columns that have 2 values only. And you can see there are 4 of them, and they're already encoded. So we actually don't have to do any binary encoding today. If we had kept the sex column on, then we'd have to do it. But luckily we had this gender ID column that had already done it for us. So we can rule out binary encoding. Okay, so binary encoding is not needed. Now the other encoding methods we can use. There is one here that I know we're going to need, which is date encoding. So currently we have these date objects. And one way we could use these as features would be to sort them in order of recency. So maybe the most recent would have the highest value and the oldest ones would have the lowest value. But there's a problem with that. We miss out on a lot of the rich information that's actually captured in these columns. For example, the months are they're not just a measure of recency, but also a measure of temperature, humidity, time of year, right? There's a lot of factors that are carried by the month. The year, however, is a good measure of recency on its own. I mean, date of hire is better to look at. I mean, date of birth. Well, date of birth is also rich in information. So we want to sort of take these little individual features out of the date columns. And so what I'm going to do is create a function called encode dates. And it's going to take in a data frame, and I'm going to pass in a list of tuples called columns with prefixes. And what we'll do is when we come in, we'll start by creating a copy of the data frame, and then we're going to iterate through this list of tuples. So for every column, prefix in columns with prefixes. So we're going to get each tuple one at a time, a tuple containing a column and the prefix we'd like to use for that column. And what we're going to do is call pandas.toDateTime on df subcolumn. So this function is really nice. Let's use date of hire as an example. If I want to take x sub date of hire, currently if I wanted to extract, let's say, the year, the best way to do that would probably be to index it, maybe like this, apply lambda x, where we're changing x to x indexed from the last 4 characters. And then we get the year, like that. But this is sort of tricky and annoying, especially when we are dealing with multi-digit months that have not been encoded properly. Well, not properly, but let's say you have a 2-digit month or a 1-digit month. We'd have to actually use regular expressions to grab it, and that can be a bit of a hassle. There's a better way to do it, luckily, using pandas.toDateTime. And what this function will do is convert it to a datetime object. You can see the data type now is datetime64. And so it looks sort of still like a string, but what's nice about this is now we can apply a function to it that instead of doing x and then indexing something like that, we can actually just say x.year, and that will give us the years. Or we can do x.month, which will give us all the months, and so on. And this is a smart function that automatically picks up on the format of your dates. And if you have some weird formats, you can actually specify your own format. But it seems to be doing a fine job given these standard formats. So let's go and use this in our encode dates function. So what we're going to do is for a given data frame and column, we're going to change it into a datetime object. So we're going to take df subcolumn and turn it into a datetime version of itself. Then we're going to create 3 new columns, and the column names are going to be the prefix that we pass in and year after. So let's say a column is date of hire. We could pass in the prefix DOH, and then we get DOH year DOH month, and DOH day. Right, so we're creating 3 new columns here, and each of these columns is going to take the original column and apply a function to it that maps x to x dot, for the first one, year, for the second one is month, and for the third one is day. So we're creating these 3 new columns out of the first column after it's been turned into a datetime object. And then once that's done, we can actually drop the original column, because now we have all the information extracted from it. So we're dropping column from axis 1, and then once we've done that for all columns paired with their prefixes, we can return df. Okay. So let's see how that works. I want to use this function in our pre-process inputs. So what I'm going to do is encode dates. And well, I'll call it date encoding. I'm going to create this list of columns with prefixes that I want to pass in. I'll call it date columns, and they're going to be tuples matching a column to its prefix for every date column that we have. So we have date of birth, DOB. That's the name of our column. So we'll pass that in along with a prefix of our choosing. I'll just keep it the same, DOB. Then we will have the date of hire column, and again with a prefix of our choosing, we do DOH. And then we have, where is it? There's one more here, last performance review date. So passing that in, and we're going to map, sorry, we're not mapping here, we're actually just putting commas because they're tuples. And we're going to pass that in along with a prefix of our choosing, which can be PRD for performance review date. Okay, now we have our date columns defined. Let's pass this into our encode dates function. So encode dates takes in a data frame, in this case it's just df, and these columns with prefixes. So the columns with prefixes is given by date columns. And then this whole thing will return a data frame. So we're actually going to save the result back into df. Alright, now let's run this and take a look. Encode date is not defined. It should be encode dates, actually. Okay, here's x. You can note as we're going along, you see the date columns are no longer with us. And at the end here, we have all of the features that have been extracted from them. So we have year, month, and day for the date of birth. We have year, month, and day for the date of hire, and the year, month, and day for the last performance review. So our date columns have been encoded. So we already ruled out binary encoding, and we did our date encoding. So there's really 2 sort of classic encoding schemes left. There's ordinal encoding and there's nominal encoding, also known as one-hot encoding. So these types of encoding deal with categorical columns that have more than 2 values. For a given one, you can see we have quite a few of them. And we can get the number of values in each one from down here. So basically the question is, for any one of these, is there an ordering between the values in the column? So for example, performance score, you can see there seems to be some sort of order between these values. You can say that exceeds is greater than fully meets, etc. But for many of these, there are no ordering. For example, the position can't really be ordered. Also, we have a position ID, and let's take a look. Okay, it looks like they actually match up. We can see that Production Technician 1 and Production Technician 1 both have the same ID, but it looks like maybe there's less information being carried by position ID. So I actually might want to drop this column. We have all the information we need in position. So let's actually drop position ID. I'm going to drop it over here. Okay. And so let's take a look at let's look for ordinal values first. So let's look for values with orderings between the value columns with orderings between the values. And we only really care about the categorical text columns because any ordinal features that have been encoded as numbers are already encoded. So let's look. Position. This clearly has no ordering between the values. They're all independent of each other. State also no ordering. Zip code no ordering. Oh well, actually, if this was an ordinal variable, it would already be in encoded form. Marital description no ordering. Citizen description no ordering. Hispanic Latino no ordering. Race description no ordering. Employment status. Let's take a little closer look at it. Basically, my rule is if there's no clear ordering, it's usually safe to just go with a one-hot encoding. Yeah, so there's not really a clear ordering between voluntarily terminated and terminated for cause. I also note that this is actually cheating to keep this on. To keep this column is cheating because it actually says if they're terminated in there. So let's remove this. Let's remove employment status over here. And take another look. So we were over here. Department, no ordering. Manager name, no ordering. Recruitment source, no ordering. Performance score, yes, we have an ordering. So it looks like there's only one ordinal feature here, which is performance score. So let's take a little closer look at that one. So dot unique. And so here are all the values. All we have to do is now order them. So PIP stands for Performance Improvement Plan, and it's sort of just like a polite way of saying they're not doing well. So it's probably below needs improvement. So if we grab that list and we're going to put it up here, we'll say ordinal encoding. Here's our list. So we want to essentially create, I want to create a function here called ordinal encode. And this will take in a data frame and a list of tuples again. This time, instead of passing in columns with prefixes, we're going to pass in columns with orderings. And again, we'll create a copy of our data frame. And this time, we'll, instead of iterating through the list of tuples, column prefix, we're doing column ordering in columns with orderings. So for each column paired with its ordering, an ordering just looks like this. Right? But it has to be ordered properly. So let's actually go ahead and order it. We're going to put PIP first for the lowest, then needs improvement after that, then fully meets, and then finally exceeds. So here's an ordering. Note that if we take this list and if we call .index on it and we pass in one of these values, let's say exceeds, it will return the integer value of that value in our list, the index of it. So if we did PIP, we'd get 0. You understand? So this is essentially ordinal encoding. We take this ordering and we get the index. So over here, let's do that in our function. For each column and ordering, we're going to take the column and apply a lambda function to it that takes some x and returns ordering.index of x. So it will just send a given value within the ordering to its index. And we just do that for every column ordering pair and then return df. That's all we have to do. So let's test it out. So let's see, ordinal columns. This is going to be a list of tuples matching a column name to its ordering. So the column name here is performance score. and the tuple we're matching it with is actually, the ordering we're matching it with is just this. So we're only passing in a single tuple. So this is the column we'd like to order, and the actual ordering to go along with it. And so this function should take care of it for us. All we have to do is call it ordinal encode, pass in, it takes data frame and the columns with orderings, df, and the columns with orderings is given by ordinal columns. Alright, and this whole thing returns a data frame, so let's store it back in df, and let's take a look. So don't need that. Alright, performance score. Oh, it didn't seem to do it. Let's see what's going on here. Oh, here it is. I never actually set it equal to the column, so we want to make sure we do that. Okay, now let's try it. Alright, so we look over performance score, and you can see it has been ordinal encoded. Values 0 through 3 depending on the value within this ordering. Okay, and I guess that leaves one last type of encoding, which is one-hot encoding. So one-hot encoding deals with columns that have more than 2 values and no ordering between the values. So if we look, pretty much we can guarantee that all the remaining categorical columns or text columns are ordinal. Nominal. Nominal means no ordering. So we can basically just go through and get all these guys and one-hot encode them. However, there may also be some numerical values that are actually nominal columns. Let's see if we can find one. So if we have a numerical value, a numerical column, where the values in the column don't take on an ordering. For example, employment status ID. I realize this is probably cheating also, because this is probably actually matching up with our employment status. And the employment status is cheating, so we have to remove this as well. Okay, but let's see. So performance score ID. There's a lot of duplicates in this data set. This is actually just doing what we did over here. Wait, where is it? Hold on. Performance score. Yeah, it's basically just adding 1 to all of our values. Let me see. Performance score ID has 4 possible values, and our performance score has 4 possible values. So maybe the ordinal encoding wasn't even necessary. These are duplicates now. Oh, man. Alright. I guess we can just drop this one, just so that we can keep that on. I don't want all of our work to go for nothing. Let's just drop it, because it's just it's redundant information. Okay. So let's see. Can we see anything in here? So department ID. This one is, they're already encoded. Look at this. I didn't even notice this. So there's all these encoded features are just like encoded versions of the ones over here. So they're not all of them exactly, but many of them. So it looks like department ID is just an encoded version of department. However, this is not in its proper form, because currently the model would assume this to be an ordinal feature. Because it looks at this, it says 5 is greater than 3, so a department ID of production must be greater than a department ID of IT, which isn't true. So what we're going to do is drop the department ID column as well, because it's not accurately representing the information in the data. Alright, now can we look any more of these? Marital status ID also. We have marital description, and I believe these should be the same. We look at how many values are in here. So marital status ID has 5 values. Marital description has 5 values. So let's drop this one. Okay, let's take another look. I'm just looking for any redundant features here. So these look like novel features that are not present in any of the other columns. Yeah, and I think that's it. Now all these ones at the end, we don't have to look at the date ones because we know what those are. But absences, this is a numerical feature. The order is important, and this is just a count. This is also a count. This is a count. This is a rating from 1 to 5 probably, and that's also encoded properly. Engagement survey, this is a numerical. Performance score, we already encoded. So the rest, I believe, are one hot. The rest are, I don't think there's any more categoricals in the numerics. Yeah, because this one only has 2 values. Right. So basically, we're just looking at these guys from position all the way to recruitment source. These are our one hot columns. And so I'd like to know how many different values are in each one. So, actually I don't really need to do this because our maximum possible answer is 311. It's not really a problem to put a few hundred extra columns on our data frame, because with using one hot encoding, pandas.getDummies will do that for us. Let's say we want to take the zip code. Let's say we take zip code, and we want to get the dummies for X sub zip. Then each unique zip code gets mapped to its own column, and you can see there were 158 unique zip codes, so now we have 158 new columns added. So this is a manageable number, but if you have a cardinality of a column into the tens of thousands, often you don't want to add that many columns to your data because it will really slow down the performance of the model. But in this case, since we're dealing with such a small number of unique values, the maximum possible for a column is 300. We're just going to one hot encode them all using getDummies. Now before we proceed, I'd like to note that you can use a prefix like zip, which will just add zip to the beginning of each column so that you know where these columns originally came from. Alright, so using this, we're going to go ahead and create a one hot encode function. So this takes in a data frame and a list of tuples called columns with prefixes. Again, we're going to create a copy of our data frame, df.copy. And then for every, let's just grab this up here, for every column and prefix in columns with prefixes, we're going to create some dummies using pandas.getDummies. And the dummies are coming from df subcolumn, and will include a prefix given by the prefix that we pass in along with the columns. Then we're going to take those dummy columns and concatenate them onto the end of our data frame. So df equals pandas.concat df and dummies and side by side, so axis 1. And then once we've added them, we can drop the original column from which we created the dummies. So df equals df.drop column from axis 1. Alright, and that's it. Then we can just return df and call it in our function. So one hot encoding. And basically, we're going to do what we did here. We're going to call df equals one hot encode, pass in df and columns with prefixes. But here the columns with prefixes are going to be given by nominal columns, which we're going to construct right up here. So nominal columns is going to be a list of tuples that maps a column name to its prefix of our choosing. So let's go ahead and see how to do this. So I want to just take a look at the object columns. So we also have to do the zip column. But if we take x.select dtypes object, this will return a data frame containing only the columns from x that have an object data type. So we know that these are all of our one-hot features combined with zip, because zip is not an object column. So let's copy those, and we're going to put them up here. Actually, it'd be better to do it this way. Let's grab this select dtypes, and we're going to plug it in to our where is it? Oh, maybe I deleted it. Oh no, here it is. We're going to plug it in here. So instead of getting the number of unique values for each column, we're going to get the number of unique values for all the object columns. So dot columns at the end. And so here they are. So all we have to do is grab that, and I'm going to go up here, and in our nominal columns list, we're pasting this. Now we just have to add zip, which comes after state. Zip. Alright, now what I want to do is grab all these, indent them all the way to the left, and I want to go through and just remove all these bits off the end. Delete. Then I'm going to press home, and then we're creating new tuples out of this, pressing end, comma, and closing the tuple and putting commas. We can remove that last comma, and now all we have to do is go in and add our prefixes that we like. Oh yeah, and let's also indent these twice back over. So for position, our prefix can be PS. State, our prefix can be ST. For zip, our prefix can be ZP. Marital description, prefix can be MD. Citizen description, CD. Hispanic Latino, HL. Race description, RD. Department, DE. Manager name, MN. And recruitment source, RS. And so this is what we're going to pass into our one-hot encode function. So we're going to go ahead and run that, and then pre-process our data, take a look, and you see we now have 292 new columns. And all of these ones at the end are one-hot columns. So there's our zip codes, and then you can see that each column has now become a bunch of other columns. You'll see that all of our data is now numeric. So we're basically done with pre-processing. Very long pre-processing, but sometimes that's what the dataset requires. So we've done all of our encodings, and now let's go ahead and split the data frame. So we're going to split it into X and Y. Y is going to be what we're trying to predict. So let's say Y equals df sub, what's it called, T terminated. So let's make a copy of that and store it in Y. And then X is going to be everything except what we're trying to predict. So we're going to drop the terminated column. And I'm dropping here from axis 1. And then instead of returning df, let's return X and Y. So down here, we'll get X and Y. We look at X. X no longer has the terminated column on it, so it's one fewer columns. And then Y is going to be just the terminated column. So we have it separate now. These are our labels, and this is our feature data. And we're going to try to, we're now going to do a train test split. Train test split. So what that means is we're going to take 70% of the data and put it in the train set, and put the other 30% in the test set. And we can accomplish this with the train test split function from sklearn, passing in X and Y, and a train size. We'll do 70% for the train set, and we'll include a random state because this function also shuffles the data before it splits it. So the random state will ensure that the shuffle always happens in the same way. This can be any number. Alright, and this will return 4 new values, 4 new sets of the data: xtrain, xtest, ytrain, and ytest. And so these four are what we're going to return instead of x and y, and then we're returning it here. Actually, run this first. Okay, and then let's take a look at xtrain. So it should be the same as x, but we're just dealing with 70% of the data. And xtest should be the remaining 30%. And you can see that the indices have been all shuffled up because the data has been shuffled. All right, so this is ytrain, just the labels for the for the 70% in the train set. All right, and that's it. I guess the last thing to do is scale the data. So that's very easy. Scale x. What I'll do is pass in a scalar to this function, and we're going to fit that scalar to the train set. So different scalars will do different things, but generally the idea of a scalar is to give each column a similar range of values that it can take on. So we're going to fit the scalar to just the train set, and then we're going to transform both the train and test sets using scalar.transform. So xtest also scalar.transform xtest. And the reason we fit only to the train set is because you want to sort of proceed under the assumption that you only have access to the train set at the time of pre-processing. And I'd like to point out that these do return numpy arrays. The transform function returns a numpy array. So if we run this now, you can see, we have to pass in a scalar. So we have two scalars imported, the min-max scalar and the standard scalar. So we'll start with the min-max scalar. So I'm creating a min-max scalar and I'm pass that in here. Alright, and you can see it has been scaled, but it's in a numpy array form. So I'd like to turn it back into a data frame. I'm going to turn these both back into a data frame, and I want to keep the column names the same as they were before. So columns equals x.columns. Alright. Whoops. Alright, now run this, and you can see our data has now been scaled. And we're using a min-max scalar, so what that means is it's going to look at each column in xtrain, find the minimum, find the maximum, and then squish all the data down so that the minimum goes to 0 and the maximum goes to 1. So all of the values in here are definitely going to be pushed between 0 and 1. Now, this is a nice way to scale, but one of the drawbacks of it is that it's very sensitive to outliers. Because if you have one data point that's really far away from the others, and that's the maximum, then it gets pushed to 1, but all the rest of the data gets pushed really close to 0. Or vice versa. It could be with the minimum as well. Let's see how this performs, and then we'll also go in and use a standard scalar after. Standard scalar, if we just look at what it does, standard scalar will give each column a mean of 0 and a variance of 1. So it'll shift all of the columns over to have 0 mean, and it will scale them to have a variance of 1. So now the minimum and maximum values aren't locked between hard limits, but most of the values are going to lie between -1 and 1 in a given column. Okay, so we're going to use the min-max scalar to start though. And then we're going to train our models. So we don't need this anymore. Let's start training. So we have a bunch of models today, 5 models actually. And I'd like to sort of train them all at once. So what I'll do, just to save time a little, I'll paste this in. This is a dictionary called models that's mapping the name of the model to the actual instance of the model. And so with this, we can iterate through models.items. So models, if we look at models, hold on, let me just run this, and we look at models. Models is the dictionary. If we do models.items, it will return a list of the key value pairs as tuples. And that allows us to iterate through 2 at a time. So for name and model in models.items, we can fit the model on the train set, and then we can print out the name of the model followed by trained. So now it tells us when each one is trained. You can see they've all been trained. So now let's compare the results. So for results, we're again going to iterate through for name and model in models.items. We're going to print out the name of the model followed by accuracy, and then we're going to plug in the accuracy value formatted to 2 decimal places and as a %. We'll type .format and pass in model.score, which will return the accuracy in the case of classification. We're scoring on the test set. We're going to make predictions on X test and then compare it to Y test. And let's multiply that by 100 to get a % form. Alright, and here we can see we're doing very well, especially with the decision tree. It looks like with the decision tree we're getting 98.94% accuracy. So the last thing I want to do to see is let's try using the standard scaler and see if it affects the performance. So instead I'm going to go and change this to standard scaler and then run these again. They've all been trained, and now let's check the results. And it looks like not too much difference. Let's actually compare them. So I'm going to grab this, I'm going to paste it down there, and then I'm going to change this back to min-max. And run this, and we compare. So it looks like with the min-max, we're actually getting better results for most of them. Yeah, the only one that was unchanged is the decision tree. So it looks like for this particular task with this set of features, the min-max scaler is doing a better job. Alright, and that will sum up today's video. So thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.